So we're finally at our last coordinate system, which is spherical coordinates. So you can imagine kind of like we had polar and XY, everything was working in a circle. Spherical coordinates is basically that we're assuming things move in a sphere fashion. So all of our points are dictated by a couple different things that define a sphere. So I want to start by just kind of going over what does this system look like. And we're going to get practice kind of plotting in spherical coordinates so you can kind of get a feel for how stuff works. So we still have our x, y, and z coordinates. And you're still having some point here, which is an x, y, and z. What I basically want to do is I want to boil this down to, given x, y, and z, can I then figure out the components for my spherical coordinate point? So there are three things that define a spherical coordinate. You have rho, which just kind of looks like a P, it's a Greek letter. You have theta, which is still the same theta we're used to. And then you have something called phi. Okay, so these last two are representing angles. Rho here is the radius of the sphere. Theta is still the angle that's in the xy plane, so exactly what we're used to. It's how we move in the xy plane. And then phi is also an angle, but this is actually in the xz plane. So essentially what happens with spherical coordinates is rho is the distance out to the origin from that point. So it's basically going to be this distance here. Phi is going to basically put you in the top 4 octants or the bottom 4 octants. So either your point's going to have to go all the way down into the bottom 4, or phi goes far enough down to stay in the top 4, or maybe even it goes down directly into the xy plane. But that's essentially dictating, are you in the top 4 or bottom 4 octants? Then theta here is essentially going to swing you around to put you into the right octant. So it's exactly that same thing that we're used to. Okay. So what I want to do is I'm going to draw a couple different pieces in here. So rho is that distance to the origin. It is our radius. Okay. Phi is the angle that this forms with the z-axis. So phi is right here, okay? And now I'm going to draw in a right triangle to help me out. So if I drop this down to the xy plane, this would be some x coordinate, some y coordinate, and 0. And then we can draw that right triangle out to here, okay? This right triangle is going to be super important to help us with the conversions back and forth between the system and rectangular. So this distance out to that xy point is exactly r that we're used to from polar. And theta is starting at the positive x-axis out to that edge, okay? So what ends up happening here is, because we do have a right triangle, even though I know it doesn't look funky because we're on the angle, whatever this is going to be 90 minus phi, because these two form a right angle. So it's actually going to force this angle up here to also be phi. So we're going to need to utilize this. And then this side of the triangle is just how much we're moving in the z direction. So I'm going to copy this over here because this is going to be important for us. Here is rho. Here are the sides of my right triangle. Not perfect, but that's okay. Right angle right here. Z is right here. R from polar is right here. And then phi is this angle up top. So I've basically moved this to a flat slice. Because again, what I want to do is I want to be able to write x, y, and z solely in terms of these values, rho, theta, and phi. Okay? We do know some conversions, so I can use this triangle to help me out to get some connections between rho and phi and z and r. And then we're also going to utilize that x we know is r cosine theta and y is r sine theta from polar. So before we get that, let's just get some practice working with this system. So we're going to plot the point in spherical coordinates. And we're going to do two different examples of this. So the first one is going to be rho theta phi equaling 1 pi and pi over 2. So I'm going to start just by drawing our coordinate axes. And I'm also going to go ahead and draw all of the negative components as well. So I got that out here, this down here, and then the back one. And I'm going to make these dotted as well. And since I'm going to need this for the next one, I'm also going to cheat ahead of time and just duplicate this so I don't have to redraw it. So this will be for B. Okay. So what you should do with these is I would recommend starting by plotting your radius. And what you're going to do is you're going to plot that on the z-axis. So starting at the origin, go out whatever your distance is for rho. So in this case, that would be 1. So let's say 1 is right here. Okay. So that is my distance to the origin. Next thing I want to do is I want to go ahead and I want to plot phi. Because again, theta is going to swing me around in the xy plane. So I want to wait to do that till last. So starting with phi, I'm going to head towards the x-axis. Because remember, phi is going to be in the xz plane. So it's going to put me somewhere along this circle here of radius 1. So starting up here, since our angle is pi over 2, I'm going to go down 90 degrees, and that's going to land me right on the positive side of the x-axis. So this is my value of phi, which is pi over 2. Okay. Now I've utilized both rho and phi. I want to go ahead and from this point plot my theta value. And so in this case, our theta is going to be pi. So from this point, I'm going to swing around a distance of pi in the xy plane. So that's going to bring us all the way back over here. And so this is where our point ends up landing. Make that a different color to make it easy to distinguish. So this is our theta value. So this point here gives us 1 pi over 2 in spherical. So let's try one more. We've got rho, theta, phi, and the coordinates for this are going to be 1, 0, 3 pi over 2. So again, I'm going to start by plotting rho, and so I'm going to go out a distance of 1 from the origin up to the positive z-axis. So that gives me a distance of 1. Now I'm going to go ahead and I'm going to plot phi, and this is 3 pi over 2, so that tells me I'm going 270 degrees. So I'm going to start here and I want to head towards the x-axis, and 370 is going to, or 270 is going to land me back here. So phi goes down and stays on that circle of radius 1, and then lands right here. Okay. And then finally, theta would swing me around, but because my theta is nothing, that tells me I don't move anymore. So my point ends up landing in exactly the same spot, but it gives us different angles. Okay. So you can see that these points aren't necessarily going to be unique, which is a bit of a problem for us. So I'm going to go over just a couple little notes about this. So phi is basically going to put us in the top 4 octants or bottom 4 octants. Or technically in the xy plane, like these last two examples. Okay. Theta is going to swing around in the xy direction. To land us in the right octant. Okay. Now to guarantee we have a unique representation, we make the following restrictions. The first, we want that radius rho to be greater than or equal to 0, just like we wanted r. We don't want to deal with shooting through the pole. Same kind of idea here. Now to guarantee I'm not in this last case where I swung around super far into the back, what I'm going to do is to guarantee I'm just in the top or bottom 4 octants, I'm going to restrict theta to 0 to pi. So this way it'll either land me on the positive side of the z-axis or the negative side, and then theta will in turn swing this thing around. So phi is going to be an angle that's stuck between 0 and pi. So iPad's acting up. There you go. And then last but not least, theta is still that same angle. We're going to restrict that to be between 0 and 2 pi. And I really don't even need the equal to here because 2 pi would land me right back at the start. Okay? So we're going to utilize these restrictions. They'll still guarantee we can hit any single point we want in any of these octants, but we're not going to have repetitiveness. So now that we've got a little bit of a feel for how this system works, we're going to talk about these conversions. So if you remember with cylindrical, we could easily just replace any x by r cosine, any y by r sine, and then with z, we just kind of left it as is. And then we were able to switch over dv using r, dz, dr, d theta. What we basically want to do is the same idea here. Can I figure out a way to switch back and forth between these coordinates? And then also, what happens to my dv? Does stuff get introduced like it does with cylindrical? So we're going to work on that aspect now, and then we'll talk about setting up integrals with it. So we want to figure out how do we convert between rectangular and spherical. Okay. So I'm going to need that same picture as before with my right angle. So I'm just going to redraw it here. We have our right angle that has r, this is z, and then the hypotenuse of this triangle is exactly that radius rho. And then phi is the angle up here. So this was that piece we were looking at before. So I know my x is equal to r cosine theta. And my y is equal to r sine theta. This is how I'm going to be able to get that theta value in. But what I don't want is I don't want this r here because that's dealing with polar and cylindrical coordinates. I need to get this in terms of theta, phi, and rho only. So that's where this lovely triangle now comes into play. So if you think about sine of this angle, phi, that's equal to opposite over hypotenuse. So opposite hypotenuse. So what I can actually do is solve for r. My r is going to equal rho sine of phi. Okay? Which is great because this r is exactly the same. I now am going to be able to get x and y purely in terms of rho, theta, and phi. And so I've got x and y done, but I need to figure out what happens with my z component. And so the same kind of thing, I can just use cosine of my angle. So cosine of phi is adjacent over hypotenuse. My adjacent side is z. My hypotenuse is rho. So that gives me that the z coordinate is rho cosine of phi. Okay. So utilizing these two and utilizing that r is rho sine of phi, we get the following conversions. Our x coordinate is r cosine of theta. R, though, is rho sine of phi. So it's rho sine of phi cosine of theta, purely in terms of those three things for spherical. And then likewise, our y is r sine of theta, but replacing r by rho sine of phi, we've got rho sine of phi sine of theta. And then just from our triangle, our z is given by rho cosine of phi. So these are the conversions that we're going to utilize to switch back and forth. So when I change something over to spherical, if I've got something on the inside of my triple integral, all my x's get replaced by rho sine of phi cosine of theta, y's get replaced by rho sine of phi sine of theta, and z will be replaced by rho cosine of phi. The other conversion that comes in handy, this is a sphere with radius rho. So if you remember the equation of our sphere, it's x squared plus y squared plus z squared is equal to your radius squared. So realistically, the same formula ends up generalizing. X squared plus y squared plus z squared is going to equal rho squared. So I'll show you that still holds though, because we know x squared plus y squared is equal to r squared. We have this formula for z, and so the same generalization is really going to hold. So further, if you take x squared plus y squared plus z squared, we know that that's going to deal with our polar. X squared plus y squared is equal to r squared. So that's that. And then z, we're going to replace by rho cosine of phi. So this becomes rho squared cosine squared of phi. And then realistically, using the same exact formula we have up here for r, I can replace r by rho sine of phi. So this is equal to rho squared sine squared of phi plus rho squared cosine squared of phi. And then you can factor out the phi squared, or rho squared. You've got sine squared of phi plus cosine squared of phi, same exact angle. So this just condenses down to rho squared. So our relationship that we can use to help switch is that x squared plus y squared plus z squared is going to equal rho squared. Okay. All right. So we've got at least some conversions between these two. The main idea that this coordinate system is going to work really well for is when you have a sphere as some kind of bounds, because we know that spherical coordinates should work really good for a sphere. Because likely it's going to be that you have constant bounds, because rho is a radius, and then theta and phi are both angles. It's going to be some kind of constant bounds, which is fantastic. So So spherical coordinates will help with evaluating triple integrals over regions bounded by spheres or cones. So what we need still is we need to figure out a conversion for dV. Okay. So I'm not going to go into as nitty-gritty details of this, but basically we're going to look at a spherical wedge and we're going to approximate its volume basically using like area of a rectangle, but kind of by arc length instead. So let's figure out what that looks like. We're going to look at a spherical wedge. Okay. So I'm going to try to draw this relatively big. We'll utilize this line in the picture to our advantage. So here's our x, our y, and our z. Because we're dealing with everything in terms of a sphere, basically assuming that you have two smaller spheres inside each other. Kind of like if you were to take a tennis ball and slice it up, this is basically what we're looking at, like a really tiny chunk out of it. So it's got some thickness to it, but the edges of it are going to be curved. So essentially, if you've got that sphere going on, when I look at a spherical wedge, it's kind of a section like this. So again, it's got some thickness to it. And it's like you've taken a chunk out of a tennis ball here. Really kind of difficult to draw, so I'm going to draw another picture over here a little bit better. So this is our chunk of our tennis ball. And then to make it look 3D, we go ahead and draw in those other sides of it. And so it's kind of like a rectangle, but it's curved here. Okay. So we've got a couple different things that we kind of have to go in here. So we've got this distance here, which is basically the change in the radii. So it's going from one of the bigger radii to the smaller. So this edge is one radius, out to that corner is another radius. And so it's giving us the change in the radius here. I'm going to also avoid using deltas because we know the deltas just turn into the d whatever. So this side length will end up becoming d rho. Okay. Over here I can show you that this is the change in the rho, just becomes d rho. Right. Now what I need to do is I need to figure out what are these two other sides. So one of them being the height and the other being this side down here. So what are these two things going to be? Okay. So kind of showing you on this picture, this is that side, and then the height is this one up here. So because these are kind of curved, what we need to remember is to get this length, I'm basically going to use my arc length formula, which is going to be the radius of that circle that it's created times the angle. Okay. And in this case, the angle is going to be d theta or d phi. Right? So to give you the pieces of what each of these look like, I'm going to draw out some pieces. So here is the top of that circle, and then here is the bottom of that circle. Okay. Because this is basically the angle that's going downward, So to get from here to here, this is that change in phi. So the angle in between these two is d phi. Okay. And that length is exactly that radius rho. It might be someone that you pick somewhat inside of it, but again, it doesn't matter the point that you pick. This just ends up turning into rho. It'd be like rho I bar or rho I star, whatever we want to call it. So this side length here is going to be the radius times the angle. So rho d phi. So to give you this side view, this is rho, and this is the change in the angle vertically. Right? Now this one is that horizontal component. So the radius in this case is dealing with what's happening in the xy plane. That's r. And this angle is the one that's coming from going left to right in the xy plane. So this is actually going to be theta. So this side will end up being r d theta. So just to show you on the picture, this would be r, and then the change in the angle, theta. If I kind of look at a slice as to what's going on in this direction, if you're looking in that projection, okay, this is r here, and this is how much we're moving in the xy plane. So this is d theta. Okay. So when I want to go find the volume of the spherical wedge, we're just going to go ahead and multiply these three things together. That roughly gives us the idea for the volume of a rectangle. But again, because you're going to take such microscopic pieces, this curve isn't going to make a ton of difference. So multiplying all of them together, it's going to give us d rho. Then it's going to be r d theta, and then rho d phi. Okay. So rearranging this a bit, we've got rho, we've got r, and then typically the order we like to do for this is d rho, d phi, d theta, just to kind of stay consistent with it. But again, I can't have an r in here. Everything needs to be in terms of rho, phi, and theta, but we know what r is equal to. That's going to be rho sine of phi. And then we've got d rho, d phi, d theta. So ultimately combining those things, dv is going to equal rho squared sine of phi, and then d rho, d phi, d theta. So just like with polar and cylindrical coordinates, you get r dr d theta. Now you're going to get these two extra functions in here in addition to changing over to d rho, d phi, d theta. So just tying everything in together, and then we'll talk about how great the system actually is, even though I know it's probably a little confusing right now. It will make more sense soon. So when we change rectangular to spherical, we have the following. Our triple integral over some surface E of a function of x, y, and z on the inside, integrated with respect to dv, still is going to be determined by those bounds of E. The inside, you're going to switch over. Your x is rho sine of phi cosine of theta. Any y's get replaced by rho sine of phi sine of theta. And z gets replaced by rho cosine of phi. Then your dv switches over by adding in an extra rho squared, a sine of phi, and then we finally can integrate with respect to these three variables. Okay. So what I'm going to do is a couple different examples. The first is we're actually going to prove what the volume of a sphere is. And then we're actually going to work with the same example from our cylindrical coordinates that we actually went through with the snow cone shape. And I'm going to show you how it switches over with spherical and how the integrals end up being much nicer to go through. So the example I want to start with is we're going to prove that a sphere with radius A has volume which is 4/3 pi times the radius cubed. So I apologize also if my audio is a little bit off in this. We're right in the middle of Hurricane Milton right now too, so I think some of the storm outside is picking up on this. So let's give this a shot. So I'm going to start by drawing my sphere. And I'm going to go ahead and draw all the other axes in here as well. Just got to make these dotted. So looking at our equation of a sphere, that is x squared plus y squared plus z squared is equal to the radius squared, which in this case is a. So drawing our sphere, we've got a circle in the YZ direction, and then also a circle here, and then I'll go through the back of that, and then we've got that circle in the front too. And it goes out a distance of A in every direction. So I want to go through and I want to set this up in rectangular coordinates, in cylindrical coordinates, and then finally we'll set it up in spherical and evaluate it. So I am going to need what's going on here in the XY plane for both rectangular and cylindrical coordinates. So I'm going to draw that off to the side. So here's my XY plane, and we've got our circle of radius A. So this would be x squared plus y squared is equal to A squared. You can also use symmetry to find the volume of this thing, but just to set this up, I'm not going to. All right. So we're going to start with rectangular coordinates. We've got a triple integral for our volume determined by this solid E, and we just integrate over 1. So I'm going to give myself lots of room, and the order of integration I'm going to do is dz, dy, dx, our typical one. So I've got to start by figuring out what is z changing between, and in this case it's always going to start at the bottom half of the sphere and go to the top half of the sphere. So what I really need to do is I really need to solve this for those two hemispheres. So moving that over, this gives me z squared is a squared minus x squared minus y squared. So you get the top half and bottom half of the sphere just using plus or minus of these square roots. So in this case, the z coordinates would change from the bottom half of the sphere, which is negative a squared minus x squared minus y squared, to positive a squared minus x squared minus y squared. Now to see what's going on with y and x, I'm going to go ahead and look at my xy plane, which is that circle of radius a. So the easier bound is going to be my x bound, because that should be constants. And so the two constants x is changing in between are negative a and positive a. So these bounds are nicer of the two. Now I need to figure out what y is changing in between, and that's going to boil down to my circle. So it's going to start at the bottom half of the circle and go to the top. So again, I would have to go through and I'd have to solve this for y. It starts at the bottom half of the circle, which is negative square root of a squared minus x squared, and goes to the top half, which is positive square root of a squared minus x squared. So these are the bounds on y. And you can see this would not be a pretty integral in any way, shape, or form. That should be positive. I'll erase that in a second. Okay. So if you wanted to go through this, this would require trig sub, and it would not be a pretty trig sub, because you would have to do multivariable trig sub for it. So instead, let's go ahead and let's put this in cylindrical coordinates to see what that looks like. Because we have that circular in the xy plane. So give myself lots of space in between my integrals. And switching over the dv, it's r dz dr d theta. Okay. So beginning with my value of z, we're really just using exactly the same bounds here. And the x squared minus y squared, I guess that dropped here, would get replaced by r squared. So this lower bound will be negative square root of a squared minus r squared, and the upper bound is positive square root of a squared minus r squared. Okay. And then I'm using my circle, so in terms of my radius, it's just going out from 0 to a. So my r bounds are exactly that. Let's use orange for that. 0 to a. So z bounds are in blue, r bounds are in orange, and then finally theta bounds, we need to go completely around the circle. So our theta will change between 0 and 2 pi. This one is more doable to actually go about, because you can integrate this with respect to z. You would have rz, and then you'd have these square roots. It's a little bit nicer because this would require u sub. Okay. So let's see now what happens, because I'm working with finding the volume of a sphere. Spherical coordinates is probably going to make the most sense. Okay. And then we're going to actually go through this integral. So remember, the inside dv switches over. You introduce rho squared. You introduce sine of phi. And then you have d rho, d phi, d theta. And so I need to figure out, because I'm dealing with the sphere, what are all of these bounds going to be? So I'm going to bring this picture down to help me out. Okay. erase that piece. So starting with rho, that is the radius. And if you're thinking the radius of the sphere, it's changing between 0 and a. So these bounds are going to be 0 to a. Moving on to phi, this, remember, is going to put you in the top or bottom octants. And in this case, you're starting up here, and I need to go all the way to the bottom of the sphere. So this is going to be 180 degrees that I need for phi. So my bounds here are going to be 0 to pi. Okay. And then last up, we've got theta. Let's do those in green. Theta is what swings around in the xy plane, and I need to go all the way around my circle. So I need to get in all 4 quadrants in the xy plane. That tells me these theta values are going to be 0 to 2 pi. And so that's the absolute benefit of this coordinate system. Every single one of these bounds is constant because this is a fixed radius. So it's a sphere of radius a. The other thing that's super nice is this inside is separable. So I actually can break this apart into 3 different integrals. Rho squared will go with the rho bounds. Then we've got sine of phi. That's going to go with the phi bounds. And then lastly, d theta is just on its own with its bounds. There's nothing involving theta inside here. So when I go to integrate this, I can really do 3 separate integrals from 0 to 2 pi d theta. Then we've got from 0 to pi of sine of phi d phi. And then we've got from 0 to a of rho squared d rho. And these 3 integrals are all very nice. They're just either power rule or a basic trig function. And this first one's even better because the antiderivative is just theta. And again, you remember, hopefully this just turns into 2 pi. So this front piece, that integral is 2 pi. Going through the second integral, the antiderivative of sine of phi is going to be negative cosine of phi. And then that's evaluated from 0 to pi. So cosine of pi is -1, so you get -1. Then you've got minus cosine of 0, so it becomes +1. So this really becomes 2 pi times 2 right now. Then we've got this last integral. Antiderivative of rho squared is 1/3 rho cubed, evaluated from 0 to a. Plugging in 0 is great, so this just gives us 1/3 a cubed. So you get 2 pi times 2 times 1/3 a cubed, which gives me exactly the volume of a sphere. So 2 times 2 is 4, times 1/3 gives me 4/3 pi times that radius cubed. So really fantastic for us. So if we can use spherical, if it's going to make sense, if you have a piece of a sphere or in the case of a cone, this is going to be the way to go to get much nicer integrals to calculate. So what I'm going to do is one more example of setting it up in the same exact way, doing rectangular, cylindrical, and spherical. It is going to be the example we did in cylindrical coordinates, which is that snow cone with the sphere on top of it. So let's go ahead and give this one a shot now in our last coordinate system. We're going to find the volume of the solid bounded above. By z equals the square root of 2 minus x squared minus y squared. and below by the cone z equals the square root of x squared plus y squared. So again, just take a look back in the video if you need that good drawing of it, but I'm going to save us that time. So we've got x, y, and z. We've got our cone given by z equals x squared plus y squared under square root. We've got the sphere sitting on top of it, and it's that sphere of radius root 2. And then we also went and found that intersection by setting each equal to each other, and it ended up being a circle of radius 1, specifically when z equals 1 at the intersection. And so this helps us find those bounds to be able to switch to cylindrical, and really even to set this up in rectangular as well. So I'll draw what's going on in the xy plane so we have it, because we're going to show the setup again for all of the other coordinate systems. We've got our circle of radius 1. And this is as far as we go in the xy direction. All right, so setting this up in rectangular coordinates, our volume is given by a triple integral again. Give lots of space, and we'll do dz, dy, dx. Our z is going to start at the cone and go up to the sphere. So the z bounds start at the square root of x squared plus y squared, and they go to the cone, or to the top of the sphere, 2 minus x squared minus y squared under a square root. Now, for what's going on in the xy direction, we have to figure out with this circle. We used symmetry to our advantage here, but I'll set it up without using symmetry. The x bounds are the nicest because this is a circle of radius 1. The x bounds are from -1 to +1. So for the y bounds, we've got to go from the bottom of the circle to the top of the circle. So starting down here, we go up to the top. And so you'd have to solve that equation for y, take a bunch of square roots. The bottom of this is negative square root of 1 minus x squared. And then the top is going to be the positive square root of 1 minus x squared. Okay. So that would be that volume in rectangular coordinates. Then I'm going to set this up in cylindrical because, again, it's got polar in the xy direction. And this is the one that we did actually integrate through, required a u-sub. So setting up our triple integral, the inside became r, dz, dr, d theta. And then here the only difference is the x squared plus y squared switched over to r squared. In the case of the bottom, you would be able to take a square root of r squared, so it just became r because we didn't have to worry about it being negative. And the top is the square root of 2 minus r squared. Then for the bounds on r, since this is a circle, the radius is changing between 0 and 1. And then in this case, to go all the way around the circle, your bounds on theta would be 0 to 2 pi. And then you could use symmetry to instead do 4 and just do in that first octant, you would get the same thing. So we showed that this was equal to 2 pi times 2 to the 3 halves over 2, or over 3, minus 2/3. Okay. So this was exactly what we did in the last section. What I want to do now is I want to set this up in spherical coordinates. We'll do that down here so this line isn't in the way. We'll set it up and we'll actually go through the integration to see that it is exactly the same thing. So I want to draw a couple different pictures. I'm going to go ahead and bring this one down actually. And then I'm also going to take a slice of this because we need to figure out all these different angles here. So I'm also going to look at what's happening in the XZ plane because remember that's how we figure out what's going on with phi. So here's the XZ. So if I take that slice, that XZ trace, if you remember, was the absolute value function. Okay. And then we've got the cone sitting up top. Let me make sure I use the same color, which is right here. And this is a radius of √2. Okay. So if you think of how this is broken down, this would be the line z equals x. This would be the line z equals negative x. Okay. And those two lines are going to bisect each of these directly in half. So this angle here is 45 degrees and this angle here is 45 degrees. That's really important for figuring out what is happening with phi. So we're going to try to set up the volume for this simultaneously. So I've got my triple integral. The inside changes over to rho squared sine of phi, and then we've got d rho, d phi, d theta. Rho I think is the nicest because the furthest we're going out is this sphere of radius √2. So rho is changing from 0 to √2. That's the biggest the circle's ever going to be. Okay. Then I want to figure out what's happening with phi, and that starts up here at the z-axis and it goes down. So the most it's going down is going to be to the cone. So phi will start here and go to the cone. And in this case, because it's bisecting that angle in half, the most it's going to go is an angle of pi/4. So my angle for phi changes between exactly that, 0 to pi/4, starting here and going to the bisection of the XZ plane. Then last up, we've got theta, and that's where I go ahead and utilize what's going on here. And so theta starts, and I need to swing all the way around. So this is what's going on with theta. I need to get completely around my cone, so it will change from 0 to 2 pi. Okay. So the bounds in this case are, again, all constant bounds, which is way nicer than this example up here because this required a u sub. So I'm going to show you this leads to exactly the same thing. It works out nicely again that the inside is separable. So I'm able to do this with 3 integrals. We've got 0 to 2 pi for the theta bounds. We've got 0 to pi/4 for phi, and the function dealing with phi is sine of phi. And then we've got from 0 to √2 for rho. So again, all really, really, really nice integrals to go through. First one we really just did, and again, this just turns to 2 pi. Antiderivative of sine of phi is negative cosine of phi, evaluated from 0 to pi over 4. And then this one's going to be 1/3 rho cubed, evaluated from 0 to root 2. So plugging in these bounds, we've got negative cosine of 45 degrees, that's negative root 2 over 2, minus negative cosine of 0, so that becomes plus 1. And then here we've got 1/3, and then really that's root 2 to the third. Minus 0 does nothing. If you left it like this is perfectly fine here. But I do want to show you it is exactly what we got before, so I'm just going to do a little bit of algebra manipulation to get to the same answer. So just rewriting the order of this, that's 1 minus root 2 over 2, which is 2 to the half over 2. And then this one, this is 2 to the half to the third, so that becomes 1/3 times 2 to the 3/2. Okay. And then really just distributing that, because the 2 pi out front is exactly the same. We're going to distribute this to the 1 and then distribute it to this piece as well. So you end up with 2 to the 3/2 over 3, which is exactly what we had before. And then when I distribute this, you're going to be left with a 6 in the bottom. And then we go ahead and add these exponents together. So that gives me 2 to the 4/2 in the top and 6 in the bottom. And 2 to the 4/2 simplifies, that's really 2 to the second. So that's 4 over 6. And then really that ends up just simplifying to 2/3. So this is 2 pi times 2 to the 3/2 over 3 minus 2/3, which is exactly the same answer we got using cylindrical coordinates. Okay. So again, you want to be very familiar being able to write these in all of the different coordinate systems when it applies. So essentially what I'd recommend doing in your homework, even though it's not necessary for you to be able to solve the integral, if it's asking you to find a volume, set it up using all three. Just do your best with it. If you can't figure it out, just let me know, and I'm happy to look over stuff for you.